Anybody have any homework questions? I put them up sort of late yesterday. Um, okay, well, I'm done talking about circular motion. And that means we're done with 2D particle kinematics. 2D particle kinematics featuring circular motion. So now, yes.
I was looking at the notes from yesterday. They don't seem to be the same notes. I wouldn't have got confused. Oh, I think you put up your status.
Oh, okay. That one would help. Okay. Okay, I better fix that. Although it's good to know some statics. Do you have a question? Yeah.
A question about, like, for example, number one, like, how do you find the tangential direction? Because, like, does it depend on the same sign of angular velocity and angular acceleration for the same signs, or no?
So if it's
like, for example, number one in this case,
yeah,
where, like, I know the centripetal of it, I cannot tell. We're on the
yeah,
the middle of the circle. We don't know, like, if it's going, if the perpendicular is going to go.
Okay. Yep. So if the rotation is slowing down, and that if the rotation is slowing down, that can either it can say that, or equivalently, alpha and omega have opposite signs. Then the tangential acceleration is opposite the velocity.
Okay.
So if it tells you whether the object's speeding up or slowing down, you can use that information to tell you the direction of the tangential acceleration. If instead it tells you the directions of the angular acceleration and angular velocity, then you can use that information. Okay. All right. So the next topic is particle kinetics. And it's a really unnecessary pain that the words kinematics and kinetics are so similar. But kinematics is just describing motion. And so that's relationships between mainly position, velocity, and acceleration. Displacement is also part of it, and well, and I guess time is part of it. Kinetics is kinematics plus the causes. So for us now, we're gonna introduce mass and force. Later on, it'll also include energy. But in other words, kinematics is the easier subject and the longer word. but the longer word. I always used to say it as kinematics is the one that's easy enough that your ma could do it. But I've recently felt sort of bad about saying it that way, so I'm not going to write it down. So if you tell anyone I told you that, then I'll just deny it. That's true. That's true. No one has enough energy to go to the video, though. Okay, so the heart of particle kinetics, the big equation that we'll get to, that we're heading towards in particle kinetics is Newton's second law. We're gonna use that all the time. I'm gonna abbreviate it N2L, Newton's second law. There's also a Newton's first law and a Newton's third law. Those are like warm up and cool down. The heart of it is right in the middle. And Newton's second law says this. I'll tell you what all these individual terms mean, but the net force is equal to the mass times the acceleration vector. Okay, and these have very specific meanings. So F net.
Can you go up?
Yep.
Yep.
Okay. F net is the sum of all the forces acting on the chosen object. This idea of a chosen object is going to be really important. We're going to put a lot of effort into being very clear to ourselves about what we're choosing to isolate, and you can use Newton's second law on a person or on a person's arm or on 6 people. So it doesn't have to be like a thing. It can be a collection of things or a part of a thing, but we're going to be very clear to ourselves about what we choose. Yep. Yes, we are. Thank you. That's worth. Yes, that's worth. So it's important. Yep, it's important that the whatever object we isolate, we're treating its location as the center of mass. And since we're still doing particle kinetics, that's kind of the way we have to treat everything as we're following the center of mass. So F net is the sum of all forces acting on the chosen body. M is the mass of the chosen body. The acceleration vector A is the acceleration of the center of mass of the chosen body. And so a big part of what we're going to do is try to develop some habits that'll help us be very clear to ourselves about what we're choosing to isolate. So now in order to, okay, and let me say one more thing about this. In order to do the math here, we're going to have a force vector, an acceleration vector, and we can't represent those vectors as components and do math with them until we choose a coordinate system. That's always true of vector components. Okay. And
what does a COM?
Center of mass. And So to do this calculation, this is only going to hold in what's called an inertial reference frame or an inertial coordinate system. Okay, so if you're not in an inertial coordinate system, this won't hold. All right, so I have to define three things before we can start using this at all. Let's see. So we need to define three new things. The first one is the mass. The second one is the force. And the third one is an inertial coordinate system. What does that mean? That has come up briefly before. Do you remember where it came up before? No, it was in those kind of problems where you're dropping something in an elevator and or in any kind of accelerating thing. And if you drop something and it's in free fall, its acceleration is down at 9.81. But if your coordinate system, and for a coordinate system, think of like a video camera, if your coordinate system is fixed to something that's accelerating, then that coordinate system is not going to observe a free fall acceleration of down at 9.81, right? We saw that with the problems where you're in the elevator and you drop something. If it's accelerating, then the camera in the elevator doesn't see down at 9.81. And that's because the elevator, if it's accelerating, is not an inertial reference frame. Okay, so we're going to be a little more clear about that idea here. Okay, I'm going to start by defining mass. That's the simplest of this three. And mass is a positive scalar, so there's no such thing as mass direction. Something just has mass, and it can't have negative mass. And it indicates the resistance an object has to acceleration. Which you can also think of as a resistance to changing velocity. So if something has a big mass, a high positive scalar represents its mass, it's very resistant to changes in velocity. If it has a small mass, it's very easy to change its velocity to make it accelerate. So like if a balloon's coming towards you and you hold out your hand, you barely even feel the contact, and you drastically change the balloon's velocity, right? You make it stop really easily. If a train's coming towards you and you hold out your hand, then the train's velocity is not adjusted at all by squishing you to the ground. So for example, a marble, it's easy to change its velocity. And so that is an indication that it has a small mass. A semi-truck, it's hard to change its velocity. And that means it has a large mass. And this is really almost the entire reason that when there are collisions between like a small car and a big truck, a small car always gets damaged really badly, and the truck, not so badly, or the things inside the truck, because the car, they're going to collide, they're going to apply equal and opposite forces to each other, and that same equal and opposite force is going to accelerate the car a lot, and the truck is not going to accelerate much. And notice pull that out. This is for later. Okay. Weight and mass are different things. They are related, and so that's why it's easy to get them confused. And like bathroom scales have a switch on the bottom that lets you go from kilograms to pounds. That confuses this stuff too, because pounds is a measure of force. In other words, that's measuring your weight directly, and kilograms is a measure of mass. And so when you switch that switch, your scale is telling you it's measuring two separate things. It's not really. And it's always just measuring the force that you're applying to the scale. So it's really measuring the weight. The weight is the force applied to an object by gravity. Okay. So if there's no gravity, there's no weight. An object's mass, on the other hand, is a property of the object that doesn't have anything to do with gravity. Mass doesn't depend on gravity. So, for example, an astronaut's weight on the moon is a sixth as much as that astronaut's weight on Earth, but the mass in both places is the same. So what's the relationship between these two? There is a relationship between these two. Between mass and weight. And that is that gravity applies a force to an object that's proportional to the object's mass. Okay, so the same object, if you compare the weight on Earth and the moon, okay, so same astronaut, on the moon, their weight is 1/6 of their weight on Earth. But if you compare the weight of that astronaut to the weight of an apple, okay? On Earth, the ratio between those two weights is the same as it is on the moon, okay? So everything, the weight of any object in any amount of gravity is proportional to the mass, okay? I think that's all I need to say about that. The units. Oh, there was one more thing I wanted to say. You don't have to write anything down here, but so how does your scale? What's your scale doing when it converts between uh, pounds of force and mass, kilograms? What it's doing is it's assuming that you're using that scale near the surface of the Earth, you know, and so it uses the scale factor, the constant of proportionality between those two to give you a number. If you, uh, so since what it's really doing is measuring a force, if you took your bathroom scale to the moon and measured yourself, it would directly measure the amount of force you're applying to the scale. And so it would accurately tell you what your weight is on the moon. And what it would tell you is your weight on the moon is 1/6 of what it is on Earth. Okay. But if you switch that setting to kilograms, it would accurately tell you what your mass is on the Earth, but it would be way off in guessing what your mass is on the moon because it's using the wrong constant of proportionality. Yes. No, not very much. And the biggest differences in so you're right that the distance from the center of the Earth is a factor in how strongly gravity pulls, and so that's why you're saying the top of Mount Everest. That's as far as you can get and still be on the ground from the center of the Earth. Um, the difference is um, like sea level. I think it's 9.8065 is the acceleration of gravity, which we'll see is also the constant proportionality for weight. And at the top of Mount Everest, it's like 9.804 or something. Okay, so it's a pretty tiny difference, even, and that's a very extreme case. Mount Everest is, 30,000 feet above sea level. I think there are um, bigger fluctuations in the strength of gravity that just have to do with geological formations around where you are. So if there's like a lot of rock around where you are, um, there's a stronger pull of gravity, but it's small. The differences are small. So, unless you're doing something related to space travel, like getting far away from the surface of the Earth, uh, we can always assume that gravity is the same strength and get really good results. Okay, so the units for mass, uh, well, when I talk about units, I always talk about first um, the type of units you use, no matter what system of units you're in. Like I'll talk about length over time or whatever. Mass just has its own units, so that's not very helpful. But it's always units of mass. In SI units, um, that's kilograms. And it's abbreviated lowercase k, lowercase g. You might think it's sort of odd that the SI units uh, have a prefix in front of them, kilo, like wouldn't it be grams? Wouldn't that make more sense? It would make more sense to me, but this is just what it is. So we don't get to choose anymore. It's pretty well set. Um, any questions about mass? Um, this is a sort of a funny thing about mass. So I said what mass is really is a resistance to acceleration. It's It's a measure of how hard it is to make something's velocity change. And you can measure that. If you know the constant of proportionality, you can measure the mass by measuring the weight. Okay, so on the surface of the Earth or other places where we know the relationship between weight and mass, we can measure mass with a bathroom scale. But for astronauts who are, and we talked about this before when we did the problems related to the vomit comet. They're not really weightless. They're actually in free fall when they're in orbit around the Earth. They're really in free fall around the Earth. It's just that the thing that they're in is also in free fall exactly along with them. And so they have this feeling of weightlessness. But still, because they're in something that's also in free fall with them, if they put down a bathroom scale and tried to stand on it, the bathroom scale would say 0. They don't have, it wouldn't measure any weight. They're not applying any force to the bathroom scale. And people who are in this apparent weightless environment are in a lot of danger of losing bone density because there's such drastic differences in the forces that are being applied to your body. And so it turns out that it's super hard to measure your mass when you're in orbit. And besides that, it's much more important to measure your mass when you're in orbit than it is in other places. So that's a pain. That's a bad combination. And so how do they measure mass? They can't do it through the weight. So they actually do it with a machine that I've never seen it work, but it accelerates them. It applies known forces to them and measures how much they're accelerating, how quickly their velocity is changing. I picture it like one of those things like 50s, like Sears used to sell, the 50s housewives, like, you know what I'm talking about? I don't really know if it's like that at all, but I like to picture the astronauts in their leotards and stuff on that thing. But anyways, so that's the way to directly measure mass. Apply forces and measure how much those forces cause acceleration. Okay, next thing we have to talk about is force. And this is a bigger topic. This is going to take more time. Mass was a scalar. It's just a positive number. Force is a vector. So it's a vector quantity. It measures the intensity of push or pull on an object. If you think about something coming into contact with an object, so forces are caused by contact between bodies, except in a couple of cases. So imagine like contact. It makes sense that that forces have a directional, contain directional information. If something runs into you from the back, you fall down forward. If something runs into you from the front, you fall down backwards. And those are different based on the direction of the force that's applied. If all we want to know is the net force applied to an object, that's the sum of all the forces applied to the object. Then Newton's second law is enough already. We don't have to know any more about it. It's enough by itself. So for example, let's say that a ball follows the position function. So position is a function of time of 2t squared. Let's say this is in meters. This is a 1D example, by the way. That's why I don't have a position function. I just have a single value for position. And say we want to know what's the net force on this object. Let's say that we're given that the ball has a mass of 0.1 kilograms. Well, Newton's second law says that the net force is equal to the mass times the acceleration. The acceleration, well, the velocity is a function of time, is the time derivative of the position. So that's 4t. The acceleration is a function of time, is the time derivative of the velocity. So that's 4. This would be in meters per second. This would be in meters per second squared. So the net force is equal to the mass, 0.1, times the acceleration of 4. And that would give you a value of 0.4 kilogram meters per second squared. Okay, so if all you want to do is calculate the force that you get from adding all the forces together, like I didn't say anything about making that ball move that way. It could be rolling down a ramp, something could be pushing it, or something could be pushing it this way and something could be counteracting that a little bit the other way, you know. There could be all these things applying forces to it, but if all we care about sum of the forces, then this is enough. Okay. Units of force. Are mass times length divided by time squared. That means that SI units are kilogram meters per second squared, but that's a really messy unit to use for something that's going to end up being kind of a foundation of this class. And so this is given its own name, the Newton, and it's abbreviated with a capital N. This is 0.4 newtons. Okay, let's do a two-dimensional example. Let's say an object's moving in a circular path. And let's say that it has a constant angular velocity of 2 radians per second. And let's say we want to figure out what's happening when it's at this location. The radius is 0.5 meters. The mass of the object is 2 kilograms. What's the net force vector applied to the object at the instant shown? So again, we're just trying to calculate what you would get if you added up all the forces. And we don't know what the forces are that are making this move in this way. There could be some kind of machinery attached to it, like a Ferris wheel. It could be on a string swinging around, and then in that case, it would need a little rocket booster or something to speed it up as it goes up and slow it down as it comes down. But we don't care about, it could be really complicated, but we don't care about what's applying those forces if all we're trying to do is figure out what happens when you add all those forces together. Then the acceleration is enough. You don't have to know any more about it. So, and this is a constant angular velocity of 2 radians per second clockwise. The first thing we have to do is figure out the acceleration at this point. And to do that, I'll draw the path. The velocity is this way. The angular velocity is constant, so there's no tangential acceleration. Because that's equal to alpha times r, and alpha is equal to 0. The centripetal acceleration is this way. And we can calculate the magnitude of the centripetal acceleration as omega squared times r. So that's 2 squared times 0.5. So 2 meters per second squared. And we figured out the direction of that acceleration just by inspection, by the way we think about things in lab. So we know that that's in the negative y direction if we're using our usual coordinate system like this. So the total centripetal acceleration vector is 0, -2. And since there's no tangential, this is also the total acceleration vector at that instant. At the next instant, it would be something else because the centripetal is pointing towards us, from a different spot toward the center. But this is at this single instant. And now Newton's second law says the net force vector is equal to the mass times the acceleration of the object. What did I say the mass was? 2. So 2 kilograms times an acceleration vector of 0, -2. And so you get a net force of 0, -4 newtons. Or you could think of it as 4 newtons in that direction. You know, that doesn't say that there aren't forces pushing to the side and pushing up and all these different things. It's just saying that once you add up all these different forces in all these different directions, they come out to 4. Okay, and notice that Newton's second law holds each instant. So in other words, this isn't necessarily the force vector, the net force. At a different instant. Okay, any questions about that? Yes.
So for net force, you're a person riding on
Yes. Well, you know, actually, now that I think about it, I guess I would say not quite, because you tend to feel contact forces from individual forces. You know, so like if you had one net force that would produce this acceleration would be a an upward force of 1,000,000 pounds, let's say 1,000,000 newtons, and a downward force of 1,000,004 newtons. Okay, and the combination of those two forces would smush you flat, you know, but the acceleration of your smushed carcass would still be this, you know. So it's what you feel in the sense that um, it produces the acceleration that you feel, but the contact forces are also something that in engineering applications we're really concerned about, because it often determines whether things are going to break and that kind of stuff. Yes.
The only time, if it doesn't show you the angular acceleration, you only have given the angular velocity. That means it'll be constant, right?
I should say it. So
Yeah.
I went back and said it later, that it was constant. I was just being a little sloppy there. It was clear in my mind. Okay. So the next thing we have to talk about is we're usually, and it really that last example kind of brings up the importance of this. Usually what we want to know is we want to know things about individual forces. Knowing the net force really isn't usually what we're looking for. So unfortunately, we usually don't want the net force. We want individual forces. And so next class, tomorrow, that's what I'll go into. So next class, we'll start separating FNet into individual forces. Okay, any other questions? All right, see you tomorrow.